if you're going to start any industry, what you should do is first find an industry that has a lot of money. Two is find a problem that really doesn't have a good solution to it. But we use half-pipe reactors, but
Yeah.
the problem was they take so long to weld. So that was the solution I attacked. Well, let's increase the weldings. So really, you have to find a problem worth solving. It's a lot of times we'll solve problems and was it really worth the squeeze because you waste all your time. The hardest part is going to be convincing someone to change what they're already doing.
This episode is sponsored by Latticept, a consulting company for the oil and gas industry and a distributor of the GPU native Lattice Boltzmann code, MSTAR. In today's episode, I'll be interviewing Ben Turner. Ben attended Georgia Tech and has over 14 years of experience in the oil and gas industry. He's the holder of several patents and is the founder of Latticept. I hope you enjoy our conversation, and please like, subscribe, and hit the bell so you don't miss an episode. Thanks for joining today, Ben. It's good to have you.
Yeah, thanks for having me.
Absolutely. Can you give us a 1 to 2 minute intro of where you started in CAE engineering and where you're at now?
An interesting story, actually. So I originally went to this welding school, and then I went to Georgia Tech. And at Georgia Tech, I took an elective on CAD and FEA, and I thought, well, we'll be learning how to use an FEA program. And really, we learned how to kind of write one, which is not really what I wanted to do. When I went to work for Lindy Engineering, we did a lot more fitness for service, finding element analysis type of pressure vessels. And so that was like my first industrial experience to FEA was at Lindy Engineering. I joke, but I'm also kind of not joking. I got yelled at by Germans for 5 years because when you first touch an FEA tool, it's like any other tool. You make pretty pictures that are ultimately but kind of garbage. I mean, until you understand the codes and the rules and how all this works, make a lot of stuff that's not very good. There, I also got experience with CFD, which I've always been interested in because I think I saw the videos of space shuttle, you can see the plasma coming off. Like that must be incredible how they did that with the computers. And it was always kind of like academic level stuff. Like, well, if you worked for NASA, you could do this. But there they were using, Lindy Engineering was obviously very well funded. So we had, hundreds of cores that I could at least borrow for, and get a taste of CFD. So that's kind of where I started using it industrially. First in college, you kind of, they always had the academic version of COMSOL that you opened and I don't know how to use this. But really I got a taste of Fluent, I guess, when I worked at Lindy Engineering. So that's like my first exposure.
So how did you get to where you are now?
Yeah. So it's an interesting story, at least I think. So I actually got hired at Lindy Engineering because I went to welding school. We made pressure vessels. So we actually made small modular hydrogen plants out here in Canton, Georgia. We shipped them. We were exporting all over the world. So we were probably one of the only companies, this was in 2014 when I stopped working, exporting to China. So we exported tons and tons of hydrogen plants to China because they were using it to upgrade the diesel to get the sulfur out. We were exporting it to Russia, all sorts of places. So it was a really neat job that I got to build the hydrogen plant. I did, me and another, funny, his name was John Thomas, but he's a completely different John Thomas. I worked with an engineer named John Thomas who came from Westinghouse, who basically taught me the ASME code. So I was able to do all the piping analysis, pressure vessel analysis, and get to see it built across the street. So that was cool. What happened though was the oil market basically tanked, and we used to have like the euro was strong and the dollar was weak, and it completely inverted. And so we went from like 10% raises to, we might have to lay you guys off. So I went to Harvard Engineering, which is in Johns Creek. And honestly, I started off as a kind of a spec sheet guy, like filling out spec sheets. And I hated it. Terrible. Just filling out data. Just not good. So I realized, well, either this is going to be my life or I'm going to create my own position. That's kind of what I did. So I convinced Hargrove to invest in ANSYS Fluent, ANSYS Mechanical, and then I started basically what became, now it's known as the Advanced Solutions Group. I don't work there anymore. Obviously, I started Latticept, but that's how I evolved to where I am today. As pressure vessels, I used finite element analysis as kind of a wedge to break myself into fitness for service, because that's You got to have FEA to do fitness for service if you got a corroded vessel. And then I use that to kind of leverage further to start doing CFD analysis at Hargrove, and that's what I ran in for. So that's kind of the chain of how I got here.
Yeah. No, thanks for the intro. And really, really interesting. And I want to dive into this more too. How did your training as a welder shape your perspective as an engineer? And just context for me asking this question, I grew up on a farm and my dad taught me how to weld, did some welding in the oil field for some summer jobs in high school. But I'm really interested on your take on that.
Yeah. Okay. The first thing about welding that will teach you is that being really good at engineering, being really smart, doesn't mean anything if you can't put it together. At the end of the day, if you put something on a piece of paper, doesn't mean anything. And you learn a lot of respect for blue collar guys by learning to weld, and having them across the street from me. When I worked at Lindy was a huge help because one, they weren't shy about telling you were wrong. In fact, they were kind of looking for that. And if after you got your feelings hurt a couple times, if you then approach them, like ask to them, how would you do this? And then you use your engineering knowledge with theirs. Not only they're going to respect you, but now you build a better product. So really welding, this really kind of gave me a realistic approach. Like a 32nd of an inch is tiny. It's probably not going to happen on a piece, even if you put it on a piece of paper, right? Like it's not going to happen. So yeah, I really think it gave me, and I think employers know this because that's all they want to talk about is welding. When I went to go get interviews, like, oh, you can weld, you can actually do something, right? I mean, that's really helpful.
Yeah. No, that's such an interesting element that I found is critical too. I did a lot of construction observation even after I finished my master's degree, and I definitely have been yelled at by plenty of senior superintendents, contractors on the site of just because you draw a line on the paper doesn't mean it's going to happen. So I can
Yeah, exactly. Yeah, and
totally relate.
you get kind of a feel for metal, and you really do. Like, you literally can bend a piece of metal if you go out there with your hands. So if you say, someone says, have you analyzed that? Like, well, it's half an inch thick and it's holding 100 pounds. I probably don't need to do that. You kind of get an understanding of that's a big deal over there. This isn't, and you piece that together so that you're putting your engineering brain on the hardest problems, not worrying about, a 1-inch drain valve or something. Not that that's important, but you can use a rule of thumb to move on.
Yeah. And I think that's something that a lot of people struggle with. And this kind of goes into the next question, more about just field work in general and how it's shaped your approach now that you're a consultant to approaching problems and sifting through, okay, what are the big things we have to get right? Not, like you said, not that we're ignoring the other stuff, but just allocating resources properly and not getting fixated on some minor details that can be taken care of without being over designed. Or can you just speak to that though a little bit
Yeah.
more?
Here's a perfect example. So I did a lot of pipe stress using Seizure too. This is a perfect example of a tool that's really fast. So pipe stress analysis, you're trying to balance thermal expansion with pressure stresses, basically. So you put in a lot of piping loops, so that when it grows, your nozzle loads aren't too high. Now, what you can do is you can sit there and you can mess with the gaps. So you can say, oh, I'm going to put a guide here and I'm going to put a stop over here, and it's going to be an eighth of an inch, whatever. Well, I remember setting up this one heat exchanger and I spent days on it. I got all the guides just right. And then they sent it back to me, probably a year later, and they had just welded every single one of those guides together. So at the end of the day, if it's not clearly communicated, this is important, or, maybe they don't even think it's important, or maybe it isn't. It really doesn't matter what you put on a piece of paper if some dude's just going to weld it all together, which is exactly what happened. Now, ironically, it didn't fail either. So again, it goes back to like, well, what was I really doing? Was I just fiddling with numbers? Was I actually engineering? Was all of that analysis just for naught? It's kind of an interesting thing when physics actually meets reality, what happened. And a lot of times things pass the code or don't pass the code work, and sometimes vice versa. It's just an interesting clash of real physics and engineering mathematics. And usually they're off by several factors. It's kind of what safety factor is, right?
And I think maybe you can clarify. I don't know that I caught the whole thing, but what were you expecting them to do then? They welded it together, but you were expecting them
Okay,
to.
sorry. Yeah, so I had a pipe and I had a guide. So I wanted the pipe to grow out, and it was going to stop. I had to stop here so that my thermal growth was pushed basically away from the heat exchanger. So that
Okay.
I don't have overturning moment on the heat exchanger, so you don't break a nozzle or something like that. But at the end of the day, none of that mattered because they welded that guide, they welded that shoe, they welded all that back. So all of the thermal expansion was going somewhere, and it's probably going into destruction. When we do those analysis, we just assume that the anchor is completely still. Of course, that's not real. So that's probably what happened. But it
Okay.
just goes down to like an engineer or his office twiddling with numbers, trying to get something perfect. The end was just a complete waste of time in the end because the shop guys didn't care. They didn't know. They didn't know what the point of this was. They just welded it all together.
Yeah.
So
Well, and I loved what you said earlier of when you took your questions and got their feedback. Like, yeah, this was right at the beginning, right? If you had a question, you took it to them and said, "Well, how would you do this?" And that tight combination, right? Because it's not like you're advocating ignoring physics, right? We need to use it, and certainly we're not advocating that it trumps reality. Because I've also seen that people who have been in the field a long time have a lot of experience. And so it's reconciling those two paradigms and getting the best out of it, right? Is that what you'd say?
yeah, absolutely. And most of the time, it's related to fabrication. You know,
Okay.
uh, because they being the blue collar guys in the shop kind of have a better feel like how I'm going to put this together.
Hmm.
I'm going to put like, well, I have this complicated, maybe I have a distribution pan inside of a nozzle or something. And they look at it and say, well, how am I going to put that in there? I mean, well, I didn't think of that. We'll have to cut it apart and put it through the manway or something like that. Well, then now we have to bolt it together. So now it's got another steel. So now it leaks, just all this different stuff that to me is like, I put a nozzle inside the vessel. What's the problem? But in reality, that's not how it works. Someone has to literally put all this together and assemble it. And the assembly really is where the blue collar guys, in my opinion, help because they know how heavy all that crap is. They know how they're going to have to hold it, how they're going to have to move it. And that really is where they shine, at least, from an engineering standpoint.
Yeah, that's interesting. I have this graph. Well, it's a Venn diagram, and it kind of describes the ultimate value of CFD. And this is one of the things that I try to articulate, but you just did it much better than I did. That you've got the physics, right? We've got to understand the physics, and on this side, you've got to understand the problem you're trying to solve. But then down on the bottom, you've got to understand how it's actually being built or constructed or manufactured, right? And if you miss that piece, then it's just not practical.
Right.
Just like if you miss the physics piece, then it's just not reality. And if you miss the problem piece, then it's useless because it doesn't actually address the root issue. And it's like this perfect trifecta of all those three circles overlapping of what a good design is. And anyway, yeah, excellent explanation. So transitioning back a little bit more, you started doing FEA at Lindy, right? Had you had any introduction to it at Georgia Tech, or had you had any classes where you kind of covered finite element or?
So actually, my first exposure to finite element was actually electromagnetic. Um,
Okay.
so years ago, I've always been interested in electronics, microelectronics, and stuff like that. So I was doing something with electromagnets or something, but there was a program I could download and you could build a little coil and you could tell how many turns it had and you could just visually see the electromagnetic field. I remember thinking like, wow, this is huge. Like there's no way I could solve these equations by hand. I don't even know what they mean. All right. So that was kind of my first exposure to like computers doing something really hard. So then when the elective was offered at Georgia Tech, I took it. We learned UGS NX at the time, which is extremely powerful software. I just never used it again.
Yeah.
Almost exclusively use Ansett Mechanical. What used to be Algor. Now I think Autodesk bought it. I don't think they still use it anymore. I think now they switched to Nastran or something like that.
Okay.
So FEA introduction really wasn't until industry, which honestly was probably better because building something with an actual ASME code that you're going to put into service that someone stamps their name. I built this. To me, that means a little more than doing a homework project.
Yeah.
And ASME codes are very rigorous for a reason.
Yeah, that's cool. So, what are some common misconceptions that you've seen about pressure vessel design or pressure vessel analysis as you've worked in the industry over the years?
Let me start. So,
Here comes the list.
yeah, I mean,
Get your pencils out.
so here's the thing. When you see a pressure vessel that has a square knob, one of two things happen. Either that guy is at the top of his field, because the square nozzle has the weirdest stresses on it possible. Or alternatively, which is 99% of the time, the guy who built this has no idea what he's doing. And that usually is what happens because I've repaired or seen crack or have analyzed more square nozzles than I can, care to talk about because it's a stress concentration at the corner. In fact, uh, one time this paper company called me and they had a huge, everything in the paper industry is huge. The 24-inch, 30-inch pumps. And they had cut a hole in it, and they called me on the phone and said, cracking. And I said, why is it, what did you do to it? Well, cut a square hole to get into the pipe, and now the hole we cut is cracking. Well, make it a circle. Okay, that's basically it. That's the end of my consultation. Make it a circle, and it fixed it. All right, so that's one thing. Square holes, stop with square holes and square pipes. Stop with that. The second thing, that really I see in the pressure vessel industry a lot that people shouldn't do. Oh man, I completely forgot after I went on my rant about square pipes. Uh, it was a good one too, and I can't remember what it was. Square holes and flat plates. People, every time I design a custom opening or something, someone wants a flat head or they want a flat plate because it's easy for maintenance guys to grab it and pull off of it. And every single time I give them something 6 inches thick, and they're like, why is this so thick? And I explained to them because it's pressurized. If it's not a circle, it's going to be one. So in the pressure vessel industry, we don't use flathead. Look at a blind flange. They're like 4 inches. So square tube, square hole, and flat plates are like the two most common things I see all the time that you should stop doing. Just stop with the flat plate. And I said that because there's a guy, David Turner, I just worked with. And we went back and forth with the client. They really wanted square plate for their little filter thing. They wanted doors they could just pull off. And I built it curved to match the shape of the vessel. And it was 1/2 inch thick. And I was like, all right, I'll give you a flat one. Here it is, 3 inches thick. How are you going to lift it? How are your maintenance guys going to pick it up now? Well, yeah, I mean, that's the difference.
Okay. So that's the solution is curved. Are there any reasons why someone might, is there any practical reason or maybe physical reason why someone wants a square pipe?
They're easy to make. I
Okay.
mean,
Just manufacturing.
yeah, you have to roll a circle. I mean, it's really not that hard, but people will, it's easy to cut a square. It's a lot harder to cut a circle. And I've tried to cut circles doing acetylene toward, I can't, I mean, don't get me wrong. I'm not saying like, oh, it's easy to cut a circle.
Yeah.
But from a stress standpoint, you shouldn't do it.
Yeah. Okay. No, that's good. That's really, really good to know. What about from an analysis standpoint then? That's the design standpoint.
Oh,
What
yeah,
about
yeah.
from an analysis standpoint? What are the misconceptions there?
So there's a lot of misconceptions, and I've made some of them myself. So one big thing is when you're using shell elements, there aren't peak stress. Like that's not a thing. So
Okay, and I'm new to FEA. So shell element, maybe for a beginner.
sure. So you start off, basically you have beam elements, which we use for pipe stress is literally just 2 points on a line. The shell element will be you assign some thickness to it, but it's still basically just a sheet membrane, so to speak.
Okay.
And then a solid element will be, a tetrahedra or something that you broke up.
Okay.
The first thing that people always do, well, here's it first. Introduction to FBA, don't use solid elements the first time. Like everyone wants to because they look cool. Like, wow, this mesh is amazing until you hit the solid button and it's like 300 days, like some crazy amount of time. Two, the post-processing is a lot more difficult because you have to separate out the stress. Like you need to know what a peak stress is. Peak stress is called fatigue. And then the opposite, what a lot of people will do is they will use a shell element and they will have some high stress and they'll say, well, that's a peak stress. Well, that one doesn't. Like, well, no, I'm sorry. That one does count because Shell elements don't report peak stress. They report membrane and bending stress. So in the ASME code, you have three different types. You have membrane stresses, you have bending stresses, and you have peak stresses. Elements assign these differently. And so linearizing and classifying these elements are extremely important, and it's done wrong all of the time, including, I'm sure in some of my work I've messed it up. Yeah. So that's like the number one thing I see is classification of stresses just done incorrectly.
Okay. And maybe to dive into this a little bit more, what do you feel like is the cause of classifying them incorrectly? Is it, and again, I'm just not as familiar with this process. Is it, okay, I'm using a shell element and it's just the way the equations are doing it? Because you said shell elements don't report the peak stresses. So it's actually the computations they're doing just don't spit it back out because they're not including it because of the way the boundary conditions are assigned and the assumptions in using the shell element itself, right? It's
That's
a
right. Yeah.
0D.
Yeah, when you use a shell element and they're glued together, you're not explicitly modeling that junction.
Okay.
So that junction is going to give you the stress concentration factor, which is the peak stress. And you need that in order to calculate peak stress. So it goes both ways. If you use a shell element, two shell elements glued together, and you haven't done any analysis down here, the actual junction, you can't tell me it's good for fatigue service. And vice versa, if it's in fatigue service, and you don't classify I think I said it backwards, but long story short, you have to make sure your elements are reporting peak stresses and vice versa. If they are reporting peak stresses, you need to know that counts for fatigue and you have to take it into account.
Okay. That's good things to watch out for common mistakes. So switching gears here a little bit, Ben, I think I had reached out to you. It's coming up on 2 years now, almost 2 years, about MStar, and you had started using MStar, and I just remembered. Yeah, just describe what it was like for you using MStar for the first time, having used other tools, and what sold you on it?
Yeah, I mean, I will talk a lot about this. So, in the consulting world, you get a lot of really weird projects, so to speak. And the client always wants it very quickly, which is fine. I mean, they've got plants to run. So what I was looking for was actually something for my own project. So when I worked at Hargrove, I patented something called the Omega jacket, I think is what I'm calling it. It actually will, from the Boltzmann reactor, it will have an Omega jacket, which is a unique type of half-pipe jacket designed for the chemical industry. Long story short, in order to develop this, I needed to calculate thermal stresses very quickly, transient thermal stress, because that's what causes it. Oh yeah, you have localized transient thermal stresses. In order to calculate the local transient thermal stresses, you have to calculate the transient fluid field very, very quickly. And you can't do that with finite volume method. And I know because I tried. And even I even tried scaling it up in the cloud with hundreds of cores, or whatever. But when I first got MStar in my hands, couldn't believe how fast it was. I mean, just insane. Like we could do a third mixing tank, and that's not even what I was interested in, but just knowing that you could solve this mixing agitator equation or, set up with full LES turbulent and you could just spit it out and everyone can understand what's going on. You can add particles and stuff. I knew that this was something else. So when I talked to John on the phone, I was like, I mean, the software is incredible, but I can't really use it because what I'm looking for is heat transfer. And John, we went back and forth. He said, I think we can get heat transfer to work. And we did pretty well. I won't say it's 100%, but it's at least enough that I can calculate local heat transfer coefficient and use that data to dump it down. So my first experience with MStar was like, I can't believe it's this advanced and I missed it all. Like this didn't come out yesterday. It's been around for years. How did I not discover this sooner? And I think it was just because it was kind of hidden in the pharmaceutical industry until recently. Is what really why I missed it. I don't do anything for I'm not until now. So
Yeah. Yeah. So isn't that one of the things that you've authored a paper on, right? The
that's
heat
right.
transfer coefficients, and you got that published, and maybe you could talk about that a little bit and what the finding was with what you're able to do
Yeah, it was really interesting. John Thomas, he wrote most. So I found the coefficient and a correlation in some paper and brought it to John. So
Okay.
it was really based on he had a generalized mass transfer coefficient in the particle solver. So he had some correlation both based on the local eddy dissipation rate and the local kinematic viscosity. You could calculate some generalized mass transfer. So I looked at that paper and the guy was talking about, well, this also applies to the heat transfer, dot, dot, dot. So there was a generalized heat transfer coefficient in that paper. Well, John kind of handed that to John. He ran with it, and just showed that, yes, there is actually a generalized Nusselt number coefficient correlation that we can use in an LES simulation to calculate the local heat transfer coefficient and use that in our transient thermal analysis. So that's kind of the gist. So we looked at a single pipe. I think we looked at a coil, an agitated coil. We looked at a tube bank like you would have in a superheater or something like that. In every case we looked at, if we look in the free stream and we get the eddy dissipation rate and the kinematic viscosity, and we use that number to calculate the local heat transfer coefficient on the wall, it was plus or minus, I think, 20% for every correlation that we tested. Some guys on the internet be like, 20%, oh, that's not that close. But if you look at a heat transfer correlation in a book, they're all over the place. I mean, some are plus or minus 100% or more. So the fact that every single one that we tested was just one equation, I mean, it's kind of a big deal. At least we think it is.
Yeah. Yeah. The universality of that within that range is really impressive. Because what were you doing before? I mean, it's another way to look at it too. Of well, what was your option before this implementation and this methodology? And it was depended on which textbook you picked, and doing some local approximations by hand.
That's right.
Based on whatever output you got, and that's not only time consuming, but
yeah, and my geometry is weird. It's like a half circle. It's shaped like an omega, if you can imagine that. So
okay.
we've done some labs. So originally I did it in Fluent. You have to have really, really fine boundary layers, and they're pulling the reference temperature from some Y plus region of the boundary layer. And there's all these, don't get me wrong, the math is incredible. And it ended up being dead on because I built a lab test to prove it. But one section of Omega Jacket is one thing versus an entire wing wrapped around a vessel. That's an entirely different problem now, and it's heating up transiently. So I'm able to take something very complicated and break it down into basically just one correlation that close enough for my, utility. It's a big deal.
Yeah.
So that's kind of what was done previously and what we do now.
Yeah.
I mean, MSTAR, we use them, these semi-empirical expressions from heat transfer coefficients books. If you've got this specific configuration of the geometry, you can use this Nusselt number coil. That's cool, and it's very impressive from a scientific standpoint, but it's not general. So if I add these physics to it, I don't know if it's still going to work because I've completely changed the original, experiment.
Yeah. Yeah. No, that's interesting though. And especially I think it's one of the things that I think I'm getting better at personally. I didn't start this way, but just identifying that when we talk about CFD and the way we're using it, it really comes down to using the right tool in the right way for your objective, right? And especially in the type of work that you do, that I can see why that makes a lot of sense, because you need the transient for the system that you're trying to analyze, and you don't have time to run, like you said. From an estimation standpoint, do you even know what it would take in terms of running the finite volume in Fluent?
No, I mean, so that's a good point. So I literally, I took the vessel. So I ran, 10-foot section in ANSYS. I'm not sure a day or something to solve. That's no problem. But then I took the same boundary layer configuration. I took the same mesh size. I dumped in my CAD model and I started the meshing. And I came back the next day and it wasn't even halfway done meshing. It was like, just kill this. Like, this is never going to work. I can't even get past the meshing part. So, I mean, weeks, if not longer, which I can do now on a day. That using a desktop computer.
Yeah. So maybe this is a good time to segue of why did you decide to start Latticept?
Yeah, there's a lot of things that kind of collided at once. One, and I mentioned him already. His name was John Thomas. That was my old mentor. So then the new John Thomas showed up, and you ever seen The Matrix when they're like, follow the white rabbit, and that guy shows up, or the girl shows up, and she's got a tattoo of a white rabbit? I believed in science. So when another guy named John Thomas shows up with this incredible CFD software, it's like, I should pay attention to this John Thomas because the old John Thomas told me a lot. Like, kind of a synchronicity thing in the universe. Like, there's a reason these people are named the same thing, right? That's kind of weird. So not that John Thomas is some rare name, it just anyway. Um, so when he showed up and when I started using Instar, I was also at Hargrove, kind of running my own consulting firm internally anyway. I was doing, talking to clients and pricing stuff out and then doing all the work myself. It's like, why am I doing this? I can do this myself if I can get the clients. And so I thought, you know, having John Thomas. So actually, John Thomas actually approached Hargrove to sell MStar. That was actually the original ask was, Hargrove would be a great partner to sell MStar. And for whatever reason that didn't fit in their business model, but I jumped all over that because I knew what this was. So now I have a link to an industry, I have legitimacy through John Thomas, and I have this experience doing consulting work anyway. Now I think is the time for me to leave. It didn't hurt that my wife also at the time made really good money. So it's not like I was, risking homelessness or something. So just a combination of lucky factors together.
Yeah. So maybe just for clarifying a little bit more introduction to the John Thomas co-founder of MStar, maybe we better give a little background to the audience here so they can keep these John Thomases separate and understand.
Sure.
I don't know if you want to take maybe a minute or two.
Yeah. The new John Thomas is the John Thomas. He's done a lot. Apparently he started in molecular dynamics and then he worked at the applied physics laboratory where he met Kevin Smith and they co-founded MStar. And then they hired Brian Devin Sanchez, who was the solver genius. And I don't like the genius word, but he might be one because he's written the entire solver by himself. So Kevin and John went off to start MStar, and they were all CPU based. Brian showed up and GPU-fied it all, and that's when it really just exploded. So that was basically the three people that were there when I showed up. That's who John Thomas is, and now we've been acquired by Dotmatics, and now he's running MStar himself, and I do most of the sales and support for new clients in North America.
Okay. Perfect. Yeah, thanks. I should have taken care of that earlier in the show, but
Sure.
glad we got that straightened out so people can follow the storyline. So coming back to Latticept then, what problems and industry does Latticept specifically specialize in? Because you've got your consulting work that you do, but then you've also got, as you just described, that you distribute most of new software licenses for MStar through North America. So what does Latticept specialize in?
It's kind of a weird thing. It's like Latticept, most of my money comes from consulting, equipment sales, and software sales. So what I specialize in really is solving the hardest problems for industry. And that's kind of goofy. I kind of hate saying it, but it really is what I'm doing. Like, the hardest problems need computers. They need CFD. They need whatever. And that kind of all filters up to me. And I, use all the computers around me to solve that. And I had some really good engineers too. So Latticept really is about transforming industry using computers, And people think like, oh, well, computers have been around for 30 years. But if you go to some sites like 1980 out there, like the pressure vessel industry doesn't have a lot of automation to it. So that's the next thing I'm doing. I'm building a pressure vessel shop. I think the announcement will be out soon in Alabama. I'm partnering with a pressure vessel shop, and we're going to build probably one of the world's most advanced pressure vessel shops using automation. We're going to use robots, and we're going to use computer vision, and we're going to use all these things that people they don't spend the time to sit down and figure out. but they can transform their industry. It just requires such an upfront investment that I don't think a lot of people really get it, so to speak. But I get it, and so I'm going to do it myself.
How much do you think of that? I worked a little bit in oil and gas industry, and one of the comments that was made to me by a very senior person there, been with the company for a while, been in the industry for a while. We were talking about uh, commercial solvers versus open source. And he said, some of our clients won't take an open source CFD report. And I said, well, why? If it allows us to deliver the report at a cheaper rate, right? Because you remove the license cost. And he made this statement. He said it's very weird. He said, when you have a piece of equipment, an asset making millions of dollars a day for you, you become more conservative in what you do and how you do it and how you take things offline and when you bring them back online. Like the planning around some of this stuff just has to be so well thought out. So I'm just curious, do you see that being some of the factors in maybe there might be people who have perceived that they do need changes, but it's just balancing
Oh yeah,
turning the profit knob versus turning the investment knob. And there's all kinds of ways you can play that game, but
yeah, absolutely. I mean, you're changing something that works is a risk, like period. So the benefit of changing has to be worth the risk. What a lot of people think, you know, what I think happened is they don't realize how far technology has come in the last 20 years, and a lot of things that people thought were risk, I really don't think they're risks anymore.
okay.
Because it's come so fast, so quick. And just to
Can you
give
give
you
an
another
example?
Hmm?
Do you have like any examples you can think of that?
Yeah, example is automated welding. Like,
Okay.
everyone talks about like, oh, in the 80s we tried automated welding in automotive, and there's some really funny stories actually. You should go read it. Like the robots, like the car would come through and the robot would break a window, and then it would weld two other cars. Like this is real, like because they didn't have computer vision, they didn't have all these advanced sensors that we've developed in 30 years.
Yeah.
Now they're using robots all the time. Actually, I didn't know this, that the Fanuc robot facility is completely automated. Can run the robots are making robot, and they can run for 30 days without human interaction. Like just that is the facility in Japan making the robots. It is robot.
Wow.
Yeah. So he said, I know this because the Fanuc guy just showed up in my office to talk to me yesterday about robots. But he said during COVID they were the only place in Japan that didn't have to shut down because they didn't have human interaction. They'd only had to show up to feed more materials into the machines. So, I mean, that's pretty crazy, I think.
That is insane. Okay. So that's one big thing.
CFD
Technologies. Yeah.
is another example. Like 10 years ago, CFD was like right on the edge of utility, like where I could buy a computer for $10,000 and I could sit down and I could make something that didn't require a PhD. Did I have to check it? But now, of course, with MStar, you can solve things so quickly that you can literally just sit there and play with it, Or instead of running one simulation with one agitator speed, well, what if we did a sweep of 30 different agitator speeds? Just see what happens. Hey, let's find out. So now I think CFD is that next level of technology, basically with these GPUs where we're just going to start just discovering whole new areas of the design space that we never touched before because we didn't have time to explore it. You know what I mean? Why would we deviate from, like you said, our industry knowledge when we know that 30 RPM worked or whatever? Why would we try 32? Well, because it was a risk, and now it's not a risk. So we've got computers. We can adjust agitator blade, angles to find exactly what works the best. That's really what's going to happen next, I think, is we're going to start squeezing 1 or 2% more out of a plant that's making millions of dollars a year, and that's paid for itself 100 times over. You know what I mean? Like that's when people are going to get it. Like when you can start doing that, and we can. So that's the next frontier, I think, is this whole GPU computing thing.
Yeah. So what is maybe the coolest or maybe your favorite problem or most unique problem you've solved at Latticept? You talk about kind of hardest problems, but is there one that really stands out to you where you're like, you know what, that was just fun. That was just cool.
Yeah.
Or maybe that's every week. So it just kind of becomes
No,
normalized.
no, it's not every week. The last one I did, and I kind of did this actually. So I built uh, a miniaturized thermal oxidizer. So I have to be careful, but basically, there's a company making flu vaccine, and the waste disposal unit was basically melting itself. They say it wasn't melting itself. When I was there, I saw it. It was basically glowing red. So what happened was the guy who designed it put a very large burner in a very small space, like
Okay.
14-foot flame length in an 8-foot box. So it was literally melting the back of the box. And so the first thing I did was I sat down. MSAR doesn't do combustion yet. We're working on it, but I sat down and flew it and did a combustion analysis to show that the back wall temperature was like 2300 F, beyond any metal. Right, we're way in the alkaloid range. So I designed actually a ceramic, like a U-shaped chamber, so the flame canal is now U-shaped, and then that doesn't go through another U-shape, and then that heat is being used for something else. But basically, I was able to miniaturize the thermal oxidizer into a very small. And so that was probably the hardest and most interesting problem that I've solved since I started to come.
That's cool.
It
That
just
is really
happened to
cool.
use CFD. It happened to use my knowledge of alloys, and I used some refractory that I only would have known about if I'd been in the hydrogen industry. It's one of those, combination factors.
Yeah. So one of the other things that I observe, and this is it's something I think is obvious to you because of the way you started, but I get a lot of questions about how do I learn CFD? How do I get started? And one of the things that I think people forget is it's the reality of thresholds, right? You can be the most brilliant person in the world in CFD, but unless you understand the industry and the problems that you're using CFD to solve, it, you really won't be able to create value. And so some of the things that come out of just our discussion and many discussions we've had together are you understand material properties in metals, right? You started out welding, you understand it, you've been in this industry, and it's the combination of those things. And so I guess what I'm really asking you is maybe what advice would you give to people about starting in CFD? Because a lot of things I think people miss is pick a domain and just be an expert in that domain. And it sounds like that's what you've done, right? You're not worried about solving every CFD problem you can. You have said, I'm all in on these things that relate to these specialties. So,
I mean, really, if you're going to start any industry, what you should do is first find an industry that has a lot of money. That's going to be number one, all right? I mean, being in oil and gas is pretty easy. They got lots of money. Two is find a problem that really doesn't have a good solution to it. Um, but we use half pipe reactors, and that's been the industry standard for a long time. But
yeah.
the problem was they take so long to weld. So that was the solution I attacked. Well, let's increase the welding speed. So really, you kind of have to find a problem worth solving. That's a lot of times we'll solve problems, and it wasn't really worth the squeeze because you waste all your time.
Yeah.
And two, and honestly, the hardest part is going to be convincing someone to change what they're already doing. And that's really where you have to develop these soft skills that every engineer ignores until they go into the career, that you actually have to talk to people. You have to convince people that your ideas are good, not just show them an equation they do not care. At the end of the day, if you don't really compel them to change, they don't care what your numbers say. I mean, that's kind of the advice is, and I know that wasn't super clear, that I would give someone if they were trying to start a new business. Yeah.
No, I think that's great. And especially the last point. I just had someone make a comment on some of my content, and I know it's well intended, but I just think it's funny that they said these soft skills really don't matter because you only just need the equations and the technical rigor. And my first thought was, I guarantee you that someone with soft skills is the one who signed and approved whatever budget you're getting paid from.
Oh yeah, absolutely. Yeah.
And so in a vacuum, sure, you can say soft skills don't matter, but in the way I've started talking about it is just as you want to die on the hill of conservation of mass, conservation of energy, and conservation of momentum, I can also die on the hill that conservation of financial viability trumps all of those
Oh
in
yeah.
the industry. So
If you're working with blue collar guys, I mean, bless their hearts, but they just won't do something because you piss them off. You know, what are you going to do? Weld it? You don't know how to weld, they're just not going to listen to you because they don't like you. I mean, you know
Yeah.
what I mean? So that's at the end of the day, if you can't convince people to do something for you, it doesn't matter what your equation does.
Yeah. Yep. Yeah. Good practical advice there. So, um, what is the biggest misconception people have about MSTAR? You've been using it for coming up on 2 years now, right? And what do you think? Because again, I want to be clear about this too, because we know that lattice boltzmann is good for many things, and what it's good at, it does amazing. But we also know that it's not well suited to some things. And so, what do you think are the biggest misconceptions that people have, though?
I think people don't understand how general lattice boltzmann can be, because it's basically um, we're now thinking about fluid in a probabilistic sense. I mean, we're solving Boltzmann transport equation, right? I mean, that should be general, and it is for the most part. So that's so people will see MSTAR and say, well, you do a lot of mixing tanks. And that's because a mixing tank is such a hard problem. To be able to do it that quickly just really shows the power of MSTAR. So I think the biggest misconception is just because we don't have your application in a video, which I'm working on all the time, I assure you, doesn't mean we can't do it. With that said, you're exactly right. I mean, is MSTAR the first choice for steady state pressure drop in a pipe? No. Why would you do that? There's 100 equations to do that, right? Is it suited for hypersonic vehicles? Of course not. Maybe one day, but that's not the choice right now.
Yeah.
And the second biggest thing, I think people kind of miss the point that it's inherently transient. And so people think, well, that means, if I want a steady state solution, I have to wait a long time. And that's true. But what they forget is that the hardest, most interesting engineering problems are transient, right? And so being inherently good at the hardest problem is kind of a big deal, right? So something else I solved here at Latticept was heat exchangers. They vibrate, right? And they vibrate because bubbles will form and you've got some fluid forces. And it's really interesting because in the field, you can feel like half the bubbles vibrating and the other half isn't. So one thing you do with MSTAR is you can inject bubbles and you can literally measure on the forces that the fluid acts on the tubes, and you can calculate some power spectrum, and you can import that into FEA. So when you start thinking, oh, these tiny time steps, yes, it means that it takes a long time to solve a steady state, but now we can capture phenomenon that happens that you could not capture with finite volume method implicitly. Like tube vibration, that would be impossible. I mean, not impossible, very, very difficult, right? So that's kind of the two main misconceptions of MSTAR is one, that this isn't general enough for my application. It probably is. And two, inherently transient is a huge benefit if you start thinking about the hardest transient problem of all.
Yeah, it's a total reframe of people's paradigm, right? People
Correct.
are introduced to a methodology one way, and this is no. We're not using the classical approach of the Navier-Stokes equations. We're using the Boltzmann equation, and we can prove that we can recover the Navier-Stokes equation through Chapman-Enskog analysis, right? But it's a fundamentally different paradigm
Right.
from a mathematical standpoint. So, which also goes with mixing tanks, right? Moving boundaries, it's easier. A lot of those things that not that, like you said, not that other codes or methodologies can't do, but what it does uniquely.
Have you tried doing a moving mesh in another program? I mean, it's very difficult. I could never get the boundary layers to reconfigure it. I'm sure some expert LinkedIn will school me like, oh, I do this all the time, but I could not get it as an IPSR. I push a button, it drops a moving body, and now I'm mixing a tank. Like that's something you can show someone that is working. But just sit down into mesh a tank. Then you have to mesh the impeller, which a lot of times you have to defeature it to the point where it's almost not even what it was to begin with. Then you have to add boundary layers that move with it or use some overset mesh. It's a hard problem. So that's, yeah, MSTAR really crushed that. And that's also why that's kind of the problem that John attacked. We have basically really just obliterated bioreactor market, because if you make bioreactors, you're going to have MSTAR. We can do cells, we can do particles, we can do heat transfer. We can do oxygen transport across the free space, and you can do all that in one program right in front of you. It's pretty wild.
Yeah. Yeah, no, I've done a little bit of mixing, and I always chose MStar to do it when I was doing the mixing I needed to do. And then the other times before that, I was making more coarse assumptions because I was looking at macro stuff, steady state. So I just was using like a momentum source or something and going from there. So
Yeah, and there's PhDs working on this now. You can use lattice Boltzmann methods to do FEA. You can use lattice Boltzmann methods for hypersonic application way beyond me, but you use multiple lattices that are connected like hyperdimensionally to transport the shocks and stuff like that. So going forward, really the whole paradigm rests on GPU. The fact that LBM is inherently inherently parallel, and NVIDIA showed up and gifted us with this alien level technology of GPUs. That's the two things that really are launching forward in the future. I personally haven't seen a finite volume code speed up on a GPU as fast as I can do it on MStar. Not for for some applications, sure, but for just in general, I haven't seen it.
yeah. Well, that's cool stuff. Any other unique things that you feel like people have maybe had some misconceptions about, or any other things you think we're leaving out about MStar? Strengths or weaknesses? Just full transparency of what things people ought to consider, right? Because it's
So
yeah,
MStar for sure, it has one. If you had to say its weakness, would be that at very high Reynolds numbers, we don't have the boundary layer correct. There are other LBM codes that do this, that use the detached eddy simulation, and it's like a blending of RANs and LBM. It's something that we can do. It's not what we're interested in, because we're not really interested in pure fluids. And so I think pure fluid is like aerodynamics, right?
Yeah.
The pressure distribution on a wing has to be perfect, right? Because you're going so fast. But if we get the fluid 5% right, and we also can add DEM particles, and that's 5% right, and we can do all our reactions as well. And so now we have this crazy coupling of reactions and thermal transport and mixing and all of that, ends up being within, a few percent of experiment. That's a huge deal. It's a huge deal. Yeah, we can't do hypersonic vehicles, but we can do all of this crazy physics layered on top of each other. And that's really what MStar is trying to do. MStar is trying to be a more general solution to computational physics than just a fluid solver. Yeah.
It's a great way of putting it too, because looking back in the way that I really appreciated using it was doing reaction kinetics and other things of looking at, oh my gosh, this is so easy to just type in my reaction equations and with the LES, like you said, the inherent, LES. So yeah, awesome. Well, thanks for the discussion, Ben. Really appreciate it. If someone is interested, reaching out to you, get a 30-day trial, what's the best way to reach out?
Go to Latticept.com. It looks like Lattice Point. That was a complete accident. So I originally named the company Lattice Concept, and I was like, oh, that's too long. I'll just glue them together. Latticept became the, and there wasn't a domain registered. That's very important in today's industry, obviously. So Latticept.com, and you can just fill out a form, and I'll email you. You can find me on LinkedIn too, and just DM me. I'm always on the computer. What I do.
Sounds good. Well, thank you again for joining the show, and really appreciate it.
Yeah, thanks a lot. Thanks for having me.
Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.